All right, so good morning, everyone. This morning's talk will be a deep dive. If it's appropriate, we'll take up the whole 2 hours, or however long it takes. What I have on screen is not in any way related to the talk. I'm just going to do a little dolly thing as we get started. So, how did I get into this mess? Towards the end of last year, during the holidays, on my break, I was sitting in front of my computer, as many of us were, and I had just noticed how much time I had wasted scrolling through YouTube. And I remembered something that I had heard psychologists at circles years ago. They keep saying it, but no one's listening. Is that in today's society, there's no space for boredom. There's no space for frustration. There's too many distractions, and it's too easy to distract yourself into feeling like you're doing something, but you're not. So I closed all the browser windows, and I sat at my desk in my home office, and I looked around my office with all my 3D printers and the resin printers and finished projects and unfinished projects. And I started wondering to myself, like, what would excite me? What would bring me joy? What can I start working on? Robotics is my litmus test for happiness. It's one of the things that I enjoy working on the most, and here I have spent most of my vacation not working on it. So what sounds good to work on? And my half-finished projects didn't sound like much fun to work on. And so I sat there and I became bored and a little frustrated, because you have to have space for that in your life. Otherwise, like I had done during my break, you spend all your time scrolling through YouTube and TikTok, and you don't provide a space or opportunity to do anything differently. And then I remembered something. Computer, sorry, I was supposed to type while I was doing this. Sitting in front of a computer surrounded by robots, but forward. Let's see what DALL-E has to do with this. And then I remembered that Unitree was supposed to come out with this new quadruped, Unitree Go2. Let's let this image finish. Perhaps they're a little bit busier this morning. Almost there. Almost there. It's about 40 seconds. Yeah, that's pretty accurate, except for the hair.
You have to have anarchist hair, hacker.
Oh, I would rock the mad scientist here if I could, but it would end up being a little thing at the back. So this little guy, we had some posts on the forum about it. It's a strategy that's been pretty common with robotics manufacturers to get people excited about their product. I remember back with the Pepper robot and the news releases saying that it was a $2,400 humanoid that could see emotions and was programmable. And I'm like, oh my gosh, $2,400? I'll buy two. Like literally, I'm like, I'll put it all in the car. I'll have one for upstairs, one for downstairs. It'll be glorious. And then it turned out that it wasn't actually $2,400. It was $2,400 to start the process, and then it was like $600 a month for a mandatory online connection with a minimum 3-year commitment.
Oh, now it's $30,000.
And if you want to buy it out of pocket, Walter's sharing that it's $30,000. So okay, well that was kind of a bust. These guys came out, and the Go2, to give you a little comparison to the Go1. Look over there. Their previous one, it's only 1.5 years old. Their new version is $1,000 cheaper, quote unquote. And I'm like, wow, you know what? $1,600, I'll buy two. But as is often the case, there's a catch, and there's a couple of catches. The first catch, and for me at least, the more important catch, and we'll switch back to the Go1 for a second, is that when you buy their base model that they call the Air, it's You can control it with your smartphone, and it's a radio controlled dog. It's you can control it, you can drive it around. You may be able to program a script with Blockly. I don't remember for sure on the Go one. But that's it. It's locked down. The Pro comes with a little bit more processing horsepower and a follow me mode, so that it more or less follows you around when you walk around. That's usually twice as much on $1,000 but also not programmable. If you want the programmable version, you have to get the EDU version, and the EDU version starts for the Go one, I think, at 15,000, and it comes with a backpack with a Javier NX on it that you do all your programming on. Which seems kind of like a raw deal. I'm not made of money. And it turns out that the hardware platform for all three, minus the backpack, is exactly the same. They use the MIT Mini Cheetah code, MIT licensed. So some enterprising hackers decided that really wasn't fair. So they set out to hack the dog to enable the programmable features that should have been available on the lower cost ones. And they did it. They have a repository called low-level programming, and it allows, even if you purchase a Go 1 Air, to be able to program it like you could on the EDU. Awesome. So that's kind of the background.
Is there any legal issue there, or did they have, is it right, did they figure out like fair use? Something.
You know, that would be a very interesting court case to determine whether reverse engineering of the variation of MIT licensed code breaks any laws. But anyways.
Oh, that's the code.
I think DCMA says you can't hack anything, but
Yeah, well, then there's fair use.
What's
Yeah.
DCMA?
the digital
Millennial rights.
Yeah.
But they probably don't care because the high prices for enterprises and you're a hobbyist don't care.
They don't care about it.
And that's what everyone's hoping. So they've been around for a while, they haven't been shut down.
Oh, in other words, if you're a business, you're gonna have to pay, even if you download the free code.
Yeah, because that's why it's more.
They'll get you.
You're monitoring your oil platform, they want you to pay $15,000.
And that's a drop in the bucket for those guys anyway. Yeah.
Yep. So moving over to the Go2, it's different internally. They're using a Linux Rockchip 38 something system on module. There's no more nanos or orange inside, so it's different. But same Mini Cheetah platform. They've got a hold of a dog. They took a dump. They took a dump of the image, and they're actively working to hack it, which is exciting. So that's the first thing, is if you can't program it, for me at least, like, what's the point? So I'm moving on that. Secondly, the quote unquote mythical $1,600 dog. Well, first off, it's not $1,600. So if you want to purchase one and have it shipped anywhere, they charge $400 to ship it. More to some other places, but I verified through Alibaba that shipping to the US is $400. So the $1,600 dog is $2,000. Still not so bad, not so bad. The other challenge is that shipping to the US, because of US customs duties, they're going to charge you about 25% to import it. It's going to stuck at customs, have your Visa and MasterCard handy. So the $1,600 dog now costs $2,400. Now we're right at the edge of my comfort level of getting one, but if they hack it, it's a firm maybe. So to get one here, minimum $2,400 to get one at your doorstep. There is an East Coast distributor, Drone Blocks, that purchased 55 of the Pro version of the dog. So if you're more comfortable purchasing it from the US, they're getting their shipment at the end of January, I believe, and I can pass that link along if anyone's interested. Me though, I want this one. I don't want to waste money. I'm not made of money.
What's the other one? Oh, you mean they're from the US, they're gonna mark it up?
Yeah. So The difference between that and the Pro is about $1,200, almost twice as much.
The Pro, right? The Pro.
Yeah, and that one, they say it has higher quality servos and can walk faster. It's all software controlled. And it has the follow-on module. None of these things interest me, right? So I'm keeping an eye out for this. So started the journey down the rabbit hole of quadrupeds and Omniverse. So to loop back to the beginning, we've pretty much reached peak servo in terms of robotics. We've seen the combat robots and stuff for a decade now. RoboSim sells an entire line of servo-controlled, remote-controlled robots. Some of them transform from trucks into robots. It's a commodity. Yeah, even if you keep an eye out for the serial servos, they're cheap, they're ubiquitous, you can do amazing things with them. But they are limited in terms of what their capabilities are for modern robotics. They're very high gear ratio, so without the use of a load sensor or something else, you can't really tell how much force they're exerting. You can kind of indirectly imply it to a point with the amount of current drawn, but it's very imprecise. If you want to build your own type of a robot, there are lots of options online for commercial, I should have grabbed some more links, or even 3D printed quadrupeds using standard servos or serial servos. The Spot Micro one is a really cool one. You can put on a Nito LiDAR. There's even people who have put on a little arm. And you can have a lot of fun with these. There's no doubt about it. I've done many projects similar to this. But as you may have noticed with the Spot, the Cheetah, the Go2, the dozen humanoid projects that are going to be offered for sale, they use a different type of a servo. MIT Cheetah guys did it first, and they did it best. They found a large pancake VLDC motor. They figured out that they can sneak in some gears in the middle. There's room for it.
Do me a favor, can you just fill this halfway with copy? I don't need any other add-ons for this. But yeah, it's because it's mostly chocolate right now. So. Sorry.
That's okay. Low gear ratio, like 4, 5, 7. I don't even think it goes high as 9-to-1 gear ratio. And with a low gear ratio, as long as you have the motor oomph that to back it up, you can do some very meaningful estimations of the amount of force applied. The way torque and physics works, the longer your moment, the more force you have. So these wide pancake motors really put it up. And where this all comes together is, when was this written? 2015, 2016, 2016. The idea of proprioception, your ability to know what your motor is doing. With this type of a motor, with this low to gear ratio, and you know the position, you can do the change in position for velocity. You can calculate out change in velocity for acceleration, and you can have meaningful estimations of force. And you get all that with this new design. These new designs also accept 3 different forms of input. With servos, it's just position. So you have motion controllers that break out the deltas between position 1 and position 2 over time and send position information and do it. These new motors can be controlled through the input of position. You can input a velocity, or you could input a torque. You can also input stiffness and damping as part of the equation. In other words, you have complete control over the behavior of this motor in real time. Plus, you've got temperature out because they tend to overheat if you use them on. And so, when you're looking at the humanoids and the quadrupeds, this is why they're all using this motor. This is what's pretty much provided the breakthrough needed for humanoid level robots, is scaling up this idea to larger motors for use of humanoids. And they've been used in this quadruped since the MIT MIT Cheetah from 2016.
These are called, these are, yeah, brushless.
Brushless, yet brushless DC motors, the
DC
3-pole, yeah,
Is there another name for the
ELDC.
PLDC?
Yeah, so they're the ones that you see in drones, the same exact ones. I think you guys use them in RC for drive
Yeah,
or
for some
Yeah.
cars.
Okay,
Um,
yeah, super awesome. So Unitree, the guy who started the company is actually super sharp. He made his own humanoid, started a company called Unitree, and then basically now, and I don't mean to belittle his accomplishments because it's some great hardware, he's producing knockoffs of the MIT Cheetah and the Spot. So where does this get interesting for me? So first off, I've already told myself and my credit card that I'm not going to purchase it until they crack it. Also, I'm not going to purchase one until I do something interesting in software. If I buy it right now, it's a radio control car. Sure, it'll be fun for like 5 minutes, and then I'll regret spending a lot of money on something that looks cute. So I'm going to wait. That gets into the simulator, which is the next portion of our talk. And if I can do something interesting for the simulator, which basically is a dog analog, then okay, I'll pull the trigger.
Is it 3 motors per leg or 2?
I'm sorry.
Is it 3 motors per leg or 2?
3 motors. Yeah.
The Magellan contest is in April, this would be perfect. So just to put that out there.
No pressure, no pressure.
Oh,
No
yeah.
pressure. So I joined their Slack. I can't participate much, I don't have hardware, but I've been chatting with a bunch of the guys. They have an image of the dog. They're way smarter than me at this type of stuff, so I remain hopeful. But even even when we talk about programming it, what does that mean? We've got a bunch of people in the club and our sister clubs who have built or are working on quadrupeds, right? And when I first was looking into, even with the little tiny ones that I built a few years ago, I'm like, start from scratch, reinvent the wheel because it's fun. It turns out there are a lot of existing software platforms that you can leverage, including the MIT Cheetah. Their MIT license, they released all the source code for free. I'm 50-50 on whether or not the Unitree folks are using this or a derivative of it called Champ to drive their bots. So this is free, anyone can download it. Of course, it's made for the Cheetah itself. These guys a year later said, okay, let me take that and let me generalize it. So the Champ platform supports a bunch of different robots out of the box. It has a build wizard that you can start it, and it's like, tell me about your robot. Where are the joints? What is the weight? What is the joint orientation? What is your rest? And it produces a configuration file that allows you to use all of the Champ tools in your own custom robot. And they include everything for the Go1, which is hardware identical to the Go2. It even supports servobots. You don't have the proprioceptive active feedback and control that you would with the Cheetah robots. But as long as you have an IMU, you can do a whole bunch of corrections. So super cool. That's already out there. Even more recent, and this is just one of many projects where they're adding a kind of a neural spin to the framework. OCS is a whole other legged robot framework. And this guy, I don't know if I can run the test right now. In the video that I'm not showing here because I can't click play, the guy kicks the dog. And it's a standard, like we all have to be mean to them,
I
right?
know.
And it recovers. The whatever software platform they're using on the Go2, someone tried to kick it and it just fell over. But then all of these are algorithmic or procedural approaches to walking. That's why when you say start walking, they start marching in place, right? And it's cool and it works, and they can walk across disturbances and walk across steps. And so I would be a fool for not attempting to understand this by adapting it to to the virtual robot. It's already out there. People are using it today. You can do a quick YouTube search and find people that are applying it to their robots. And that's been around for years now. Now, let me go ahead. I'm going to reshare for a video so that just when I play a video so we can see it. Here's what kind of the current state of the art is right now. So this guy did a deep learning reinforcement technique. He recorded his dog walking, and then I'm pretty sure he used the Isaac Robot Simulator Gym to do reinforcement learning to optimize for the gait. And this is the result on the Go1 dog. Now, just keep in your head, we've all seen the quadrupeds walk. Check this out. That looks natural, right? So right now in the state of the art, there is this whole technique to run thousands of copies of the robot with an optimization and a reward function to derive control strategies. And it's working today. The other one I wanted to share with you, I almost posted this, but I wanted to save something for the meeting. So this is a version of the Animal, A-N-Y-N-A-M-A-L, N-A-L, that has wheels instead of legs. And they used a similar technique. They simulated the robot in Omniverse Isaac Sim. They ran the Isaac Gym, did deep reinforcement learning based on reward functions for successful tasks. And just look what this robot is capable of from a movement perspective. This is this is biologic movement. It feels, real's not the right word, but.
And even handle packages and more. Now.
Oh my God, that is.
Right, so there's one other thing there's a clip where, right, look at the control theory problem on this. It doesn't even have legs, you have wheels. So hopefully Ben is able to start posting these links to chat in case you're more curious about them. This is a rich 6 minutes describing state of the art right now. And that's just defining a reward function, and not just, I mean, there's a lot of stuff that goes into this.
But it's a reinforcement learning along with
yeah, and there's
virtual or whatever lab or something going on.
So just to wrap up this portion of WOW, through deep reinforcement learning, it has learned how to successfully navigate like this.
Wow. Who wants to program that manually?
Well, no, and that's the thing is like, this gets me excited. Now, I'm not going to contribute meaningfully to this area of research, but just to take it, to be able to integrate it, take advantage of it, these are types of things that are getting me really excited about robotics right now.
Yeah, then it's like if the hardware is there, the difficult software problem has a new solution.
Yeah, and we've all programmed advanced robotic solutions to stuff, right? And we're all painfully aware of how brittle and fragile the solutions are and the components, and crap, it could hear me just fine at home, but now here, or it could see the goal just fine at home, but under fluorescent lighting. And oh shoot, it was able to navigate just fine at home on my plush carpet, but on the short carpet here, right? These are this approach provides far more robust solutioning. And I don't even know how to describe the control theory required for a two-wheel balancing bipedal robot to pick up a box and put it somewhere, right?
Then one of the main things they have to do is properly model the device in the simulator, right? Exactly. And then they have to throw things at it in the simulator to get it to learn this, right? Yeah. So something, and that has to be done 1,000,000 times or thousands of times in the simulator. Then it comes out with its black box control theory or control system.
Yeah, exactly. So they're getting meaningful results with this right now with the tools that are available right now. I said, you know what, that sounds like fun. I'd like to see if there's, I can get my hands dirty. But this, believe it or not, isn't even state of the art anymore. We had a couple of posts, I think last week or the week before. The mobile, that's unfortunate. Okay. The mobile Aloha folks just recently released a whole bunch of videos. I don't have a visual on this, so we'll just switch back to my DreamBot. Is they built a mobile manipulator platform with 2 arms. And they teleoperated it to do a whole bunch of tasks, hours and hours of video and recorded telemetry data for pick up a glass, put down a glass, open the dishwasher, all this stuff. They then fed that video and telemetry data into a deep learning network. And the end result is that this robot can far better, it's not perfect, but far better than any previous approaches. I have news clippings and articles from like the 70s talking about robots that can do your dishes and mow the lawn, and even from the 60s and 50s, I think, about taking your kid and stuff. And we all knew they were blowing smoke. This robot is doing it. It's not perfect, but it is cooking. It is grabbing the dishes, it's filling the dishwasher through a neural approach to training through teleoperation and video, right? And then just last week, the Figure One folks, one of the dozen humanoid startups that are robot startups that are going to have a product offered, they trained their Figure One robot to make coffee by watching videos about how to make coffee. So no longer recording hours of teleoperation. And I think the Optimus folks discovered the same thing. And the way I heard it described by experts in the field was, at some point, someone tried it almost as a joke, and they were so surprised about how well it worked that it is. I'm sorry, I should have grabbed some URLs for clips for these as well. And it's an instant coffee maker, so it opens up the top, it puts in one of the cups and it closes it and it presses the button. But their claim to fame is that it wasn't teleoperated. It wasn't programmed for recording hours of teleoperation, odometry, etc. They had it watch some videos, and it did it. So, like these developments make robotics this year to be very exciting. We've had hardware for a very long time, and I know some people tend to oversimplify it with, hardware is the easy part. Reliable hardware, utilitarian hardware is still a little bit of a challenge. It's going to be a while before I can afford a biped. But you know what? If I can figure out how to do something interesting with one of these MIT quadrupeds, and they're able to figure out how to make it programmable at the entry level, that's something that I can invest a couple of bucks in to be a part of. So my rationalization for going down this path is to be able to get hands-on some of these groundbreaking technologies, and to be able to toy with some portion of them on a hardware platform that I can afford. This guy has foot pressure sensors, full proprioceptive feedback on each of the motors, position, velocity, acceleration, temperature, and force. So, I can't think of anything else I would really want to give the robot in terms of its IMU, of course, as input to optimize movement and control strategies. The other thing I couldn't figure out, now mind you, I've kind of fallen in love with this robot look, not only because I'm trying really hard not to pull the trigger and buying it right now, but since I've been working with the model so much, and I'm like, what a goofy face, right? Like the first one, the Go one's goofy as well. Like, why a spinning LiDAR, right? Like, why that? Why the monocle? I didn't know this, but just last week, where is it? Where is it? Where is it? So it turns out they have a new product, the Unity 4D LiDAR R1. They've got GitHubs, they've got access and control documentation. This looks really familiar, almost like that's the LiDAR that's in here. So now I finally realize why it has a spinning LiDAR name, because they have a spinning LiDAR product.
What does 4D mean in that LiDAR?
Here, let's go to the page and see.
Okay, all right.
Yeah,
Find
that's
out
right.
what-
That's
find
the
out
fourth
what's gonna
dimension.
be
Wormholes too.
Yeah, so it's got a spinny bit inside the plastic, and then the whole base spins as well.
Spinny bit is that
Maybe it's intensity or something.
And even though on the Go2 through the app and the interface, it's got this very voxel, very pixelated low grain output through the dog, most likely because it's not hardware accelerated. When you look at the specs and the capabilities of the LiDAR that's in it, you get a very different picture. So, okay, no, I get it. I get why it's got a spinning
That's nice.
LiDAR thing, because it's an existing product that you
What
slide
is
in.
that?
That's not one scanner, that's gotta be stitched.
Yeah, one of these
That's a whole
has
environment, right?
one of these is supposed to be one of these is supposed to show as it roams around, it builds a map. So kind of like the
You've seen one
yeah,
videos
yeah.
before, right, with a car driving or.
yeah. So it's not
Usually you see
all
it.
at once. Yeah, one of these is a little video clip where you see the little beastie driving around and filling out the map as it does.
Those, yeah, as opposed to our, traditional single plane LiDARs, those, that has a tilt mechanism, right, of some kind, and it's scanning
Yeah, so it's turning
circular and going up and down.
360 by 90.
Usually they spit out a bunch of beams at once, so there's not a second direction of spinning, they just have like maybe 12 or so.
That's
However many,
spins.
yeah.
Yeah. This one's got
So that doesn't have a
this one's
tilt.
got the
I
spinny
noticed the
thing.
tilt.
Yeah, so
It's
it
got a tilt there.
it spins vertically, and then the platform spins horizontally.
So it does go,
Well, maybe it's doing both of them.
this does a pitch, change.
Yeah, pitch in,
Oh, pitch and rotate.
pitch,
Yeah, but it's not really,
right,
it's
pitch.
just pitch, and then it's rotating,
Roll?
which is yaw. No, yaw. Yaw is this way, roll is that way.
Okay,
Pitch,
yeah.
yaw, roll.
Yeah, so potentially very interesting. I was a little disappointed as I'm sure wouldn't surprise you. Every day I check YouTube for any Go2 and Unitree Go2 videos. And someone posted that they had purchased an EDU. And the EDU comes with an intelligent sensor that you bolt to the top of the dog. So at first I was super disappointed. I think that's because the LiDAR is upside down. So it's a 15-degree tilt. So it doesn't get things really up high and close. But really, just based on the specs of it, this is real hardware. Like, it should give you real good stuff.
Which is IntelliSense, is it?
Yeah, one of those
Oh,
things, like you just kind of bolt it on top of the dog.
so a 3D camera.
Yeah, sensing camera, and then you plug it into the backpack. Yeah.
Oh, so that was, in other words, it has to be an add-on, it was an add-on.
Yeah. Okay, so that covered, like hardware wise, there's my rationalization for jumping into this mess, why I'm having so much fun. My deal with myself is that until I do just something interesting in software, I'm not buying the hardware. So how do you write software without hardware? Simulation. And there's probably a few more out there right now. The simulators that I've heard the most about would be, of course, the one that's bundled with ROS called Gazebo. This picture really does Gazebo justice. I have never seen a Gazebo simulation this detailed. And I have suffered through setting up Gazebo simulations before. And I don't mean to disparage it, like, if it's the right tool for the job, and this is what you're used to, this is great. But Gazebo is based on the URDIF file format for describing robots and scenes. And to date, no one has written an URDIF editor. So,
It's a text editor.
yep.
Nomad.
So if you're using Gazebo and if you're using RViz and you're visualizing your robot, you're writing an URDIF XML type file to describe every joint and feature and interconnection by hand.
Isn't that what VI is for?
Huh?
Isn't that what VI is for?
Oh,
Or-
yeah, text
yeah.
editor, yeah, but.
Yeah.
Okay,
so-
VI next, I'm more on
Yeah.
the VI side. Yes, but it's, I don't use this term a lot, but user hostile, I think describes it pretty well. There's a Blender tool that you can use to export a Blender scene or a robot to URDIF one way. I actually worked with this really smart kid that wrote a script for Fusion 360 that you can export. If you set it up a certain way, you can export your Fusion 360 robot to URDIF one way. But that's it. So it's, and I think it's what started to show its age. It's based on a graphics engine from 1980, I think. But it's still out there. It's still well supported. People are using it. Another one that came up in the forums last week as well is paywalled. Another real-time physics simulator. Neither one of these require a GPU for acceleration, so you can run them on pretty much anything. And again, right tool for the job, if this is where you're comfortable, that is awesome. They're another well-supported, people are using it, there's forums, you've got help. But what got me excited was the stuff that I had been seeing about, not Isaac Sim. Not Isaac Ross, hold on. Isaac Sim. So at some point, Nvidia either purchased the rights or something, or decided to extend Pixar format called USD. USD is a scene and a descriptor format that's really rich. You can describe relationships, joints, visibility. It's what Pixar used for some of their animated stuff, and so NVIDIA standardized as USB being a format, and NVIDIA Omniverse, which is their simulator package. So it imports USD, and then you can build and bolt other stuff on top of it. It requires an RTX graphics card, so any card that you purchased within the past 4 years or so should work. More horsepower, the better. And on top of that, they built a whole robot simulator platform called Isaac Sim. And all these are for free. You just have to sign up for a free developer account. And a lot of the stuff that you're seeing on YouTube and in the news, it's funny, the Animal is their front and center demonstration. When you're talking about deep reinforcement learning and you see the videos with hundreds of robots doing things at once with Isaac Sim, this is the platform they're using. The fact that you can get near realistic visuals is just icing on the cake. The visual portion of it and the physics portion of it is all physics RTX accelerated, and I'm like, you know what? That sounds a lot. That sounds like a lot of fun. So I went ahead and installed all that. The next task was to find a model of the Go2. So they have a low resolution version of the model in their URDIF package. You can download it on Unitree ROS. So they have a full URDIF description of the robot, and you can actually import URDIF. They have an Isaac importer to bring it in with all the joints and all the masses, and you could do that in a couple of minutes. That sounded kind of boring though. So I came across a highly detailed step file of the Go2, and so I brought that in. see, I'm trying to keep the portion of my screen short enough that maybe we can go a little bit farther. So I went ahead and I brought the robot in, and I spent a fair amount of time. Well, at first I divided that up into bodies and assemblies, and then none of that exported correctly. So I brought the model in. I used Fusion 360 to correct a couple of bodies that were non-manifold, meaning that the export from whatever their source system is into STEP wasn't complete. There's about 10 of those that I fixed. And then right from here, you have an option of exporting as USD. So I've gone through this process probably 5 times, not because I'm a glutton for punishment, I'm just not smart enough to get it right the first time. But there were some very important things that I had to do. The step file describes the relative position of each of these pieces or bodies from the whole, right? So there's no articulations, there's no relationship. If you open up the bodies panel, you've just got like 150 individual bodies that aren't labeled. So, and when you bring it into Isaac in Omniverse, it brings it in basically the same way. You have to define where the joints are when doing it this way. Now, that being said, not that one. One of the packages that they integrate really well with I'm logged in on the wrong one, is Onshape. We've talked about Onshape in years past. It's an online only 3D modeler. I happen to think it's super, super cool, but unless you pay a lot more money than I can afford to keep it going, all of your projects are public, which is kind of a deal breaker for some people. But they have an Onshape connector into Omniverse, such that you can bring the model in, and you can define the joints and assemblies in Onshape, and then it imports much more cleanly as a finished robot into Omniverse. And I'm not an Onshape guy, so I did everything the hard way. But at some point, I'll probably try that workflow to see, because it's very well integrated, and you don't have to do any of the things that I'm going to have to show you right now. So if you have to define the locations of the joints between each of the pieces, you have to know where they are, which means you have to start creating sketches to define the locations in 3D space. So I did that. I defined a common origin for the center of the robot, and then I set up a series of sketches to understand the location of the hip joint in 3D space, the location of a suitable location for the thigh one in 3D space. Same thing for the location of the calf or the elbow joint. So when you open up these sketches, there's measurements that tell you exactly how far down and over and out that you place the joints. The angle of the LiDAR, which is 15 degrees, modeling the location for the LiDAR in 3D space, as well as the angle of the legs. Let's talk about the legs for a second. If you haven't had the pleasure of designing robot arms and legs and simulated control, there are a couple of things that you have to know, you have to decide on. And one of them is when you're describing the angle for, and we'll just pick on this, we'll call this the thigh or the shoulder joint right now, is what angle represents your zero position, right? Now, one of the things that I've personally gotten used to is that if the leg is dangling straight down, I've defined robots where that becomes the 0-degree position. So that means maybe positive degrees is forward and negative degrees is back. Up to a point, it's arbitrary. Or maybe you define the 0 position as parallel with that from 0 to 180, right? You just have to decide. Now, in this case, I am positive that the native rendering of this leg should not be the 0-degree angle. So I created a quick sketch to find the exact angle from horizontal so that I can program it in the bot, right? The next angle is the one for the foot. And so far, my angles for here and for there, they agree with the manufacturer's ERDIC model for 0 degrees and whatever their neutral is. The part where we disagree is how you define the 0 angle for the lower leg. Now, when I look at the lower leg, I want to keep things simple. So I want to know where the center of it is. And in modeling and simulation, I probably want to simplify this a little bit. This isn't a perfect sphere. I would probably simplify this as being a perfect sphere of some diameter. And then that would mean that the 0 position for me would be when it's dangling straight down. It turns out that the Unitree folks didn't define it that way, and I'll show you how they define 0 when I bring it to the model in a few seconds. So these are some of the things you have to keep in mind. Now, when working with a real physical robot, really you could write a translator to go between anyone. It's all arbitrary, right? But it would be important for me to know how the physical robot defines the 0 angle. And so I can either go off of the ERDIF or their ERDIF file or off the physical robot. You probably want to make your simulated robot have the same 0. And I'll show you how you can do that in a second. So I've got the robot in here. I've defined a whole bunch of sketches, exported it to the USD. I can refer back to here to get the exact angles and the exact joints. Let's move over to Omniverse, which I got logged out of. That's unfortunate. Okay, we're still on our VPN. There we go. Good. All right. Let's see. All right, so what we're doing right now is through VPN, I'm logging into my work desktop in Linux using remote desktop. GNOME remote desktop to be able to control it. It's very performant over most connections, which is super cool. Let's take a look at their Go1. All right, so this is one of the models that they give you access to as their examples. And so if we look at the center of rotation for the thigh, we can see that we agree that that's a rest position. The part that I was confused by is their leg. So if we zoom in here, here is their pivot for the elbow, and here's where the pivot would be for the foot. I don't know which line that they set up. It doesn't make sense to me why, and their ERDA file for the Go2 looks the same way. How they derive defining this as the 0 position. So when I get closer to an actual robot, I might have to make some adjustments. But going back in, so after, I don't know if I want to say out loud how much work in reviewing it. I brought in and textured and colored the step version of the model. I took all 150 components, divided them into subs, and then for each one of these, manually defined the joint location using the measurements from the Fusion 360 file. And the whole thing is kind of fun. It's almost like building a robot, except you're not getting your hands dirty. There were a few more things that I ran into if you decide to jump in, and that weren't. There's a bunch of stuff that wasn't obvious. When you first get set up, it wants to render a 1280 by 720 resolution screen, which is fine. But as soon as you start sliding things around, you kind of want the display to resize. Under settings, viewport, you can tell it to, no matter what size the viewport is, to always fill it. So I'd recommend checking that off just so you're not annoyed by a weird blocky. So you've got your robot imported, you've got your, you've created a physics scene, you've created a physics ground plane, which turns on all the fun physics stuff, right? You've imported your robot, you've arranged it into pieces, you've gone in and you have defined the joints based on their locations in your Fusion 360 file. As part of the joints, you can do things like you can define your maximum and minimum range of motion, like your hardware limits. And once that's all done and you press play, if all goes according to plan, wait, let me check one thing. I'm not going to be able to drop it if the motion planner is running in the background. Okay, so if you've done everything right and you hit play, it should flop. And I've since added in stiffness and dampening and some friction stuff, so it doesn't do the kerplop you saw in it earlier.
When I was doing URDF for Gazebo, one of the hardest things was the mass and all the moments of inertia of your elements. Did you have to deal with the moments of inertia, or what did you do there?
Oh my gosh, Brian, let me speak to your soul right now. As someone who's suffered through ARVIS and Gazebo and ERDA, one of the first things that I noticed when I brought in a robot was that you have GUI access to every piece of it, from location, translation, scale, adding in and pulling in physics-based materials and color-based materials. It's all here for you to work with through the UI. That is the first thing. The second thing is that, and there was no easy way to define center of mass and those properties. Like, there was a SolidWorks thing you could do if you had SolidWorks, and that was about it. Check this out. When you're ready to apply physics to a piece of the robot, here, let me move this one here. So one of the first things is you get to define which ones of these bodies. I don't know what happened. Hold on. I clicked on something. Give me a second. All right. Is for each of these bodies, you get to define whether or not they have mass. Hold on. Whether they have mass, whether they're just there for a visual and not to include them in any mass calculations, or, as I'm sure you're familiar with collision bodies and stuff, I'll show them a different robot in a second, whether it's a collision body that's not visualized but is used for mass and collision calculations. So there's that. Next, you go and you select your, your prim with all of your visual and things in it. You right click, you're gonna love this, add physics, and then you there will be an option for physics body and colliders preset. When you do that, it calculates center of mass. It calculates the mass based on a pre-assumed mass of water, 1 gram per, but you can change that. So when you go in and you do that, it not only calculates mass, center of mass, I did it the easy sloppy way where it defines a simplified, here I'll show you. So for this guy, let me turn off the meshes. And what I'll do is I'll turn on the colliders. So by clicking on that one button, it automatically defines a default collision body based on 64 facets that you can use as a start. So I did that because I haven't defined collision body. Okay, so for those of you, when you're doing physics-based calculations, you can do it the super hard way, which is you choose every bit of your model as a collision surface, which is super slow. They figured out ways of optimizing that to get the right result out without spending days calculating. And one of those is to say, okay, here's what my robot looks like, but when you're doing collision calculations, instead of figuring out the 3D contours of the foot, let's simplify that foot to a sphere. And it really simplifies the calculations and you still get the same result out. So when I set up this robot, I'm like, I don't have time yet to define custom collision forms or bodies. Just simplify it and we'll run with it. And it does it right out of the box. Now, at some point in the future, if I'll get to it. By type physics, let me just turn off the collisions. I can go back in and I can define for the cap is all one body foot, right? I can go in and add a sphere primitive, orient it to cover the shape of the foot, and then define it as a proxy object with collision, and then it simplifies the collision as well. And it's all done from here. So I can go back in Fusion, identify the central coordinate of the sphere in the model, and then create a sphere, add it to the foot. And then in Onshape, you just define it as a solid as part of the model, and then when you're going in and you're refining it, right? Like,
Yeah. I was excited going from URDF to Exact Pro. We could, like make primitives and do that stuff.
Okay.
But this is about to do that, right?
It made it fun. Yeah. There's no longer any frustration of typing it in and then running it like, oh, I was off by a factor of 1,000, or it's and there was. I realized I'm making this look easy. There was a fair amount of getting to this point, but just being able to have access to all of the features of simulation through the UI,
That's a big.
made it a joy. And then the fact that it looks so cool is just icing on the cake. All right, so I got it in, I've got it simulated, there's stiffness and value, so it doesn't kerplomp anymore. I want to be able to control it through ROS. Now, there is a first-class Python scripting subsystem and stuff you can do within Omniverse if that's your deal. Me, I need to it needs to work through ROS, not because I'm a ROS advocate, but that's my interface on a physical robot. So, luckily, there's an app for that. So, there's 3 different types of writing code for Omniverse. The one that I used is what's called the action graph. And in the action graph, and I can't take credit for figuring this out, I followed the tutorial. You can set up an action graph to input and output ROS messages. And so one of the big ones for me was to be able to control this. Now, there is a very real possibility that the punchline to this entire deep dive was that I can't get it to move yet. I just figured this part out last night and I've been working on it for 3 days. There isn't a tutorial on how to rig a quadruped model for ROS from scratch on the internet. That's not to say that Isaac Sim isn't well documented. There's a lot of documentation, there's a lot of tutorials, but the documentation that I had to leverage to figure out how to do this was actually going into a different tutorial with one of the robots that works and figuring out what their robot had that my robot didn't. And I'm not gonna say it wasn't frustrating. There were about 4 aha moments between why doesn't this work and, oh, whew, I have something to show tomorrow. So if you're downloading Omniverse right now in Isaac Sim, or you're gonna do it and you're gonna import your own robot, first off, if you run into something, tap me on the shoulder. I'm happy to share anything I've picked up over the past couple of weeks. But there are a couple of things that you need in place in addition to the action graph that describes what topic you're subscribing to and what robot it goes to and wiring everything up. All this part is from their tutorial. And I learned it using their JetBot tutorial, and they have a Franca Panda robot that I literally dragged onto the scene, and I was bouncing back and forth trying to discern what theirs had that mine didn't. And after setting all of this up, there are a couple of lessons learned. The first lessons learned is that, at least on the ROS way, if you want it to honor a joint command message, that joint command message has to refer to, sorry, that's kind of hard to see. You have to specify all 13 joints. If you don't specify a position or an effort or a velocity for all 13 joints, it's going to ignore the message. Not obvious. Had to figure that out by breaking another example, and that was my first aha moment. Why 13 joints, you ask? Well, OCD Allen, in addition to obviously having it walk, thought it would be fun to have the LiDAR spin. So the LiDAR is on a pan joint. And so the number of required joints goes from 12 to 13. That was the first aha moment. The second aha moment, and I was literally printing out screenshots and setting them to one side. I'm like, what am I missing? Is that there are a few things you have to add into each joint that you don't get by default. The joint's defined, you let it sit, it just, it crumples, or in this case with stiff joints, it just kind of rigor mortises. There are a few more features that you have to add. And I only figured this out by looking at another robot that worked. My test case was, right, you're like, okay, what's different? So I brought in their Go1 robot, that's what it's for, and the Go1 also doesn't work out of the box. A little disappointing, but in physics, okay, you won't be able to see it here. You have to add in 2 more features. And those features are a feature called physics revolute joint. I'm sorry, no, that's what you get with a joint. You have to do angular drive, which gives you some more boxes to describe. I wish I could be more detailed, but it was literally my epiphany was figuring out to add these in. You have to add in an angular drive component to each joint, and you have to add in a joint state component to each joint. And so you have to add those in, and then you add them in, and it still didn't work. There's one more piece, and I'm not frustrated with lack of documentation. I'm frustrated with myself because it took a bit. In order for the robot to honor position, velocity, or torque commands, each joint has to have a damping and stiffness value. Now, I just pulled these 2 values from the Panda robot that worked. I can tell you right now, they're not appropriate for a robot because of the way that it's sitting right now, but it was a start and I got it to wiggle. So, and again, as far as I could tell, none of this was documented anywhere. It was just looking at an example robot that worked and figuring it out. Yeah, and it's just no dig on Omniverse and Isaac. It's a huge ecosystem. I don't want to say it's niche, because if you're using Isaac Sim, you're building a robot, but yeah. So after all that was in, all 13 joints, adding in angular and joint mode, stiffness and damping values, and running it, I can get it to wiggle. So, the code right here it isn't anything special. It's not like I'm proud of it. I actually adapted this from another robot code. This is my hello world for it. So my eureka moment at 8:30 last night was modifying their hello world code for joint control for a manipulator arm, defining all 13 joints, defining a default space, and then modifying their wiggle code to move the joints back and forth. And remembering how, okay, I'm gonna complain, how much more difficult it is to set up Python scripts in ROS2 versus ROS1. Not difficult, I suppose if you live in it, but it was so much easier to iterate. There wasn't a copying over the scripts to another location. You could make changes to scripts live and then rerun it. And now, every time you hit save, you have to do a colon build, and as far as I can tell, a resource. And it's just extra clicks. I'm sure there's a reason for it. It's much more flexible and capable, but
Do a symlink install. You can modify, you should be able to modify your stuff in place.
Symlink.
Symlink install.
well, the thing though is when you do a ROS2 run node, that ROS2 run node operates off the install folder and not the source folder.
Correct, unless you do a symlink install, and it'll copy symlinks over to the install folder, and you can modify stuff live. So that's what we
I
want.
think I got that in a tutorial, one of those
Yeah.
long, all the ROS2 tutorials mentioned that, right?
Con build
Sub-
minus symlink.
Less sim link install.
Yeah, it's colcon build minus symlink minus install.
I think that was in a tutorial.
Yeah,
I believe, I went through those tutorials a long time ago.
Like that?
that was a dash in between those two. This symlink and dash install.
Oh my gosh.
Yeah, I think that's what you want.
Okay,
I
okay.
think that is, yeah.
Because, oh my gosh, I mean, I kind of got used to the cadence, but
It's a pain, it's like tedious.
yeah.
No, you want that, definitely.
Yeah, and not like in ROS1, you could basically write scripts and it would find them. And I'm just venting for, but in ROS2, like you have to define that this script needs to be made. There's two ways to do it. And if you don't do that, it doesn't even, anyway, okay, sorry, enough of ROS2. It's I'm doing a ROS2 robot. Okay, payoff, and then we'll complain a little bit more about ROS. Go over here, we'll just run our wiggle. And here we go. So it's not a meaningful script, it's just taking each joint and moving back and forth between two values. But this is my hello world. This means that I can successfully interact with the robot through ROS2, and now it's game on. All right.
One question about you said you had to define all 13, joints, whatever, before it would go. Wouldn't you always, or why wouldn't you always do that? Or what were you trying to do before that? Like, not do that?
Yeah, so my hello world for the robot, what I wanted to do is to spin the damn LiDAR.
Yeah, just move one joint and see that work.
Yeah,
Okay,
yeah.
you wanted to, and why wouldn't it work to just do that?
Now, I can't see why it doesn't, but I lost many hours on the command line. ROS2 topic, send, and figuring out how to define the message type correctly.
Yeah.
And then like, crap, did I define it wrong? And no, it looks like there's no error. And it, for whatever reason, and there could be a good reason for it, I just don't know.
No.
The simulator only honors the joint command message if all 13 joints are represented.
And how does it know there are 13 joints? Oh, it's in the definition that there are 13 joints.
Yeah, so it knows what robot to look at, and it just looks for, it counts up the joints and the names.
Okay, so that's just sort of some sort of internal requirement.
For whatever reason, like maybe it's good,
It's consistency, right? So like everything comes at one time, it can do a step with consistent data.
You have to send all 13 joints.
Yeah,
Or all the end joints, and whatever it is.
Yeah, and I may have run into it before on Gazebo with a motion controller as well. It feels faintly familiar. If I were to guess, the rationale behind it is that whatever code you have behind the simulator manages the robot state, and if you're not sending all 13, then.
It doesn't know what the other ones are doing.
Yeah,
so
and I
it-
like, why would you care, right? Like, so I'm like, work. And so I'm looking, and so check this out, level of frustration. So, like, oh, okay, well, let's just pretend Alan's frustrated and nothing's working. Like, you're like, oh, well, let's just click here. And you're like, oh, you're seeing the joint command, right? And I LiDAR pan joint. I'm like, it's there. It sees it. And you're looking over here at the articulation controller. And you're at LiDAR pan joint. Like, you can see it. It's here. Like, the message was being passed.
Ah, that's debugged.
Right, yeah. And so how did I end up figuring that out? I took their Panda robot with the working example, and I went back over to, out of frustration, I went back over to their Hello World code, and I commented out 2 of the joints.
Stop
And I ran it,
And you're able to break it, you're like, that's it.
and that's it. That was my first eureka moment. And then after that, like, it still didn't work because there was like 4 other things I had to do.
It's like, we always should say, thank the universe for examples that work.
Yeah,
Because hobby robotics wouldn't be possible without example code.
Yeah. yeah, and I think that's kind of like, I can't recommend this solution enough. I haven't used paywalled personally, but I've used Gazebo and Erdis. Working with this was a joy. I don't want to say it's not well documented because there's examples, and examples are the best documentation you can have if you just sort through it. The one thing that I will warn you about though is that save often.
Oh, crashing.
I was watching some YouTube webinars on Isaac Sim. Some of them are very recent. They actually have a Jet Racer series. They brought in the Jet Racer and they're articulating the model in Onshape and even this guy who's an Isaac Sim evangelist sponsored by Nvidia to do webinars. It's very easy to crash. And so as a result, I save after every successful change because you never know what click is going to result in having to restart. So just make your peace with it. This isn't space shuttle level software, and just be aware that you could click on something that shouldn't have had any effect, and then you just have to relaunch the environment. The other pieces of this that, like, as an individual developer, aren't super useful to me, but with the package, let me see if I can install this a little bit. Is if you're working with other people, one of the things you get out of the box, and you have to install to get access to their sample data, is a little piece called Nucleus. It's a file store for projects and files and USD and scenes and robots and stuff. I'm not using it right now because I'm just storing it on my drive. But if you're working with a team or with someone else, it's built from the ground up for collaboration. So if you have someone who's working on the robot and you're working on a scene with the robot, when your buddy who makes a change to the robot hits save, it updates the robot in your scene that you're working on. So it's built from the ground up for collaboration, which is super cool. I wish I knew someone who's working on the same thing as me because that would be pretty awesome. But yeah, I can't recommend it enough. It has been, even with the save often, it's been a joy to work with. Because it looks more realistic and I've built this from the ground up, it kind of gives me that feeling of creation and problem solving. But yeah, now I'm set. There's still so many differences that I have to work on between my simulation and the real robot. The joint origin is certainly one of them. After the Hello World, I want the robot needs to have joint origins that have the same orientation as the real robot. Otherwise, you're running a translation layer, and there's literally 0 point. You want this to match the real robot. The second one is the messages that are passed back and forth between the real robot. They're not the out-of-the-box ROS example. So joint state, joint command, IMU. They have custom ROS messages. So Using Python, I can set up the robot to pass the custom ROS messages to give you a more real world experience. The next challenge is that the robot hardware runs, I think there's ROS2 connectors on the Go2, but all the code that I showed you, the Cheetah and Champ, it's all written in ROS1. The simulator has ROS1 and ROS2 connectors built into it, right? So when I'm looking at the big picture, I'm not really a developer, so like the prospect of converting their code to ROS2 sounds really scary and awful. So I'll probably rework this into a ROS1 bot for the purposes of taking advantage of the Champ code. The ROS2 connector on the physical dog supports ROS Humble. Another aspect to this is that the Edu version of this robot has a backpack with an Orin NX or an Orin Nano in it. And it's Jetpack is their version of the Ubuntu bundle, which is 2004. And so in order to make the robot smart, like when I buy the robot, I'm not buying any other hardware. I'm going to plug it into my computer. It's going to be on a harness and an Ethernet cable plugged in back to my computer, right? But at some point, if you want mobile smarts, you'll probably want to use one of those GPU accelerated platforms, which will be Jetpack, and you want to make sure that that version of ROS, whatever you're doing can run in that version of ROS. The last piece of this rabbit hole puzzle is that Nvidia produces their own variant version of ROS and ROS2. They do it because they need their Jetpack is on 2004 and ROS2 only runs on 2204 for those of you in the Linux space. So they have their own build farm that builds ROS2 packages for 2004. But they also have a slew of GPU accelerated packages that they maintain. So anything that you're doing in Vision, Point Cloud, all this stuff, they produce GPU accelerated versions of those packages that you would want to use on, let's say, an Orin backpack. And the Orin Nano is $400. The Orin NX 16 gig is $900, and then like the full Orin AGX one that is $2,000. That's out of my price range. But investing in even the $800 Orin NX would be a lot cheaper than the $14,000 on the dog. Which gets back to the beginning, of our discussion, where once because it's the same hardware platform, same software, once they crack it and give programming capabilities to the $1,600 dog, it's going to be game on.
Now, you said, who is it Nvidia has those different packages that
Yeah.
For all those, simulation of or the software that handles the LiDAR and all that stuff?
Mm-hmm. Yeah, here,
They're kind of like, this is right for the Orin. These are.
Yeah, here. So if you're going down this road and you're already running Omniverse, so you have an RTX card, you'll want to keep this on your radar because the GPU accelerated packages will make things a lot more efficient. There's just one more thing. Okay. So here's my robot. Now in the action graph, so I subscribe to the joint command. I also publish the joint state. I publish the camera, right? So here's all the hardware except for the lamp input. I even published the laser scan, and I published the IMU, and I published the transform tree, but you can't use that for the robot right? So from an interface standpoint, these aren't the standard Unitree interfaces, but you have a ROS interface to every part of the dog you want to control. We had a talk, I want to say 2 years ago, from the Foxglove folks. And I quipped that this is the future of ROS 2. RViz, this is their version of RViz. It's a free download, and it is superior to the RViz robot visualizer in every way. The least of which it supports a dark mode. But you have the same concept of panels. You can review the joint states, joint commands. It's taking in IMU and pose data into the scene. Because my bespoke Go2 isn't articulated with the same object origins as the ERDA file, the ERDA visualization doesn't work right now. But that's because just the way I set up my robot, but the transform data is being sent. And here's what the robot's seeing out of its front camera right now.
Yeah, you were talking about that photorealism, like it was just eye candy, but I think it's way more than that. Because you're going to use this vision to do something back in your robot, and that's where this becomes important.
Exactly. That's like one of the things that comes full circle is anything you want to do in neural involving vision. And there's when you're one of the many aspects of active research right now is the generation of synthetic data, right? So if you're following along on ChatGPT, they're talking about, you're using ChatGPT for output to train a 7 billion parameter model and its performance. Same thing with vision and odometry. There's workflows to generate synthetic vision and odometry data that can then be fed into the model. And at this level of detail, it applies to the real world. So, and there's office environments, you've seen pictures of warehouse environments, you can bring in USB from other places, house and office, a yard, grass, a field. The application of generating deep learning data or applying deep learning to the real world, this whole ecosystem makes it all possible. All the advances that you're seeing in deep reinforcement learning, they're using this platform. It makes it very exciting.
And these problems that we have, like the lighting's not the same, the window is open, I can put all those in there and put a random lighting variable. I can put furniture in and out of the way easily.
Yep.
But you have to, at some point, somebody needs to model these objects.
Yeah, and there's a huge library.
Is there libraries?
There's furniture, and you can find.
Oh, yeah.
The lighting is going to be. You can add the lighting.
You can add windows, whatever.
Yep. To put a bow on it, that's kind of where I'm at right now. It was a very exciting moment at 8:30 last night when I finally cracked the code.
Well, that's when you got the 13 monkeys of joints.
Is your LiDAR publishing right now? I wonder if you can see that in Foxglove. That would be really cool.
Yeah, so I've got scan. It's here. Do you have any ideas? I haven't gotten
In your 3D panel, if you click that in settings, you should see your scan topic down there. You can turn the eyeball onto your scan. Down right there, eyeball on the right. Click that. That should have turned. It's got a problem. But that's how you would turn on.
Oh,
it's got something going on. It's not happy.
Oh, transform.
Okay, so you got to publish all your transforms.
That's the challenge is.
Missing transform frame to.
You can change your frame to Sim LiDAR.
Oh, display frame?
Yeah.
Nope. What is it?
Nope. You get a lot of frames. Maybe down.
Oh, you know what it is? I don't. That's right. Because of the transform challenge, it locks up foxgloves, so I prefixed it so it wouldn't.
That's your note.
That's my note.
Anyways, but it's pretty good at that.
Okay. Yeah, I'm excited to try it out. But no, here, I'll show you what the hang up is. When you bring in the robot, let's turn it on for a second. When you bring in the robot, every body, every piece of it that is in the robot has a body origin, right? So where is 000? Now the challenge with the step model is that even though your leg is over here, the origin for that joint is 000. The ERDIF model isn't set up like that. And so what happens is that because they have different link origins, when you bring it into Foxglove and you turn everything on, the transform doesn't refer to changes in joints, it refers to changes in position for the links. And the changes for the positions of the links, because of different origin, are totally different. Yeah, so at some point what I might do is I might bring it into Onshape just to do the ERDIF export, so that they have the same joint origin, at which point the link transforms map, and then start putting some lamps and desks and chairs in there just to see the LiDAR image on it.
Wait, so that you have to export a separate ERDIF that's compatible with this,
Exactly.
Then your Isaac Sim has its own.
Yep, and then that's one of the gripes right now, or a possibility for future enhancement. They've been talking about it, is that the export to ERDIF is a one-way street, right? So you export to Isaac, you export to ERDIF, and never between the
You need both.
So if you make a change, you've got to kind of review them both, and they're looking to see if there's a way to tie them together such that you don't have to maintain two different copies of the robot.
That's because these things came from different origins. They're Isaac
because mine's off of their step file and their ERDIF was built differently.
Oh, I see. So if you start a brand new robot and you could define them with the same origins and all that.
Oh, yeah, and
Alright, that's sort of more of a.
kind of the administrative of.
It's a specific case situation.
And so as an example, here is what importing their Go2 ERDIF file using the Isaac Utilities ERDIF importer. So it's built in as a first-class importer. When you bring in their ERDIF file, this is what you get. And it's a good model. And so if I were to work with this one and make this joint names match the publisher, and then match this up with the native ERDIF file in Foxglove, everything would work. Even the physics would work okay. And you remember we were talking about collision objects, or simplifying the model for the purposes of collision physics. Here is what the collision meshes look like for their Go2. So as you can see, it's a much simpler model. So running the calculations on this is much simpler. And when you run the simulator, you'll see it runs at like 50 or 60 FPS, where I'm getting like 25 or 30. And that's the benefit of simplifying your model from a physics perspective.
Wait, so Isaac Sim can import the ERDIF.
Oh, yeah.
And display it. So you could have gone that way completely. Then it would have been compatible with.
Out of the box, and the whole process takes like a minute. Why did I spend several weeks doing it the hard way?
You're taking advantage
it
of
looks
more.
better.
You're taking advantage of the more sophisticated Isaac Sim.
So I never said I was smart, but I will tell you I'm determined. And so when you turn on physics on it, of course you get the ragdoll because there's no damping. or anything. So,
There's like two ways to do, you could, stick with the
the easy way or the hard way.
and the other way is sort of the newer, more advanced and more accurate
Yeah, I would argue more fun and prettier, but yeah.
and prettier.
And as a result, I understand more about Isaac and Omniverse than I did before. So, yeah, I could have done the whole thing in a few minutes and then spent the
Oh, really?
trying to figure it out.
Minutes? Oh, okay.
Oh, yeah.
Okay. Oh,
But
because
the
it's-
process of importing and coloring and doing the joints, I learned, it felt like I was building a robot.
You mean you wouldn't have to do all that joint stuff with this one?
No, it imports it from the ERDA file. Yeah.
Which is already there. Oh, I get it.
Yeah, and the ERDA file, the joint orientation matches the real dog, that matches the ERDA file on Foxglove.
Okay, you buried the lead
That's
there.
the easy way, yeah.
I would do the easy way first, then circle back.
Yeah, in retrospect, it probably would see some frustration. So right now it's game on. So I'm going to hard code a Python script that takes in the initial joint orientation after it falls to the ground and just do a simple stand-up, right? So that part of the code can be brittle. Then I'll move it over to ROS1 and look at integrating it with the champ controller. So it'll be a very exciting month, and I can't wait to show you what he's able to do next time we get together.
So, I have a question about the robot and about the Isaac Sim. Does the robot use tendon joints that have tendons, or is it, there's not motors in not in the elbow, there's no motor, right?
In the physical robot.
In the physical robot.
Uh,
Because I noticed when you're
Oh.
going through it, it said there was a tendon joint, and that sounds like, I haven't seen that inside of a gazebo, but that seems like it would match your model better.
So in the simulator, there is a whole piece for tendon management that I haven't touched yet. So I don't know about in the simulator. Are you asking about how?
I saw it in the simulator. I'm like, oh, wow, I've never seen that before. And I'm asking if the robot has tendons. And if it does, there's probably some benefit over declaring it as a motor.
I wonder, I know there's, so this, there's a motor back here that isn't modeled that does this direction. And then this motor right here handles the thigh up and down. And then this motor on the outside is connected with two gears and I guess you would call it a tendon to the back of the elbow to actuate the base. Yeah, honestly, I didn't need to use it. Now that you mentioned it, I'll probably start digging into it to see how that might apply to here. I would imagine between that and transmission, you can define the real rotation here. I'm not sure.
Because it's probably non-linear how it moves with the extension of the tendon.
Yeah, and the thought crossed my mind to model that as well, but then I'd have to write the code to keep it in the right spot.
I just gotta make your life harder. Ask you hard things, right?
Yeah, no, yeah. If I dig into anything, I'll let you know. But yeah, I didn't have to use that portion of the simulator to get everything.
You're dangling a controlled substance in front of
I
them.
know, I realize what I'm doing. And the other comment too, I realize what I'm doing.
He's a bad influence.
Although, but in a very real sense, how is that accounted for in the physical dog, right? So the control of this motor right here, if you just want to do position somewhere between 0 and 360, right? But how does defining the position of that motor in code reflect on this joint right there?
So I think it's probably non-linear. It's probably, if you've got a tendon joint with a full point, it's probably not one-to-one.
Interesting, because none of that is in the ERDA file.
Right, so it might be better in the Omniverse.
Yeah, so do they account for it like in the firmware code of the dog?
Oh, good question. Maybe not. Or maybe it is, maybe I'm wrong about the non-linear. Maybe it is perfectly just a transmission.
No, it's actually a really good question, and it went from, get around to it. Well,
It's not just a motor, it's a lever action.
Yeah, like a lever action.
So that's different.
Maybe.
Wouldn't they have to model that in the
Yeah,
actual
it could be a
firmware?
linear response with gear reduction of maybe 2 to 1 with, I don't know. Can't wait to find out.
And one more fun observation, when you did the collision model, the simple one, it looked a lot like an AT-AT from Star Wars. You could skin this thing, and it would be the coolest robot.
Right? Yeah, yeah. And the way that Ernest export works, like there's a different version of my dog where I put in the 150 bolts and screws. But because of the way that I imported, none of them kept their final position. Like I'm in it to win it, right? So there's because of the workflow, even though there's not a direct two-way connection between here and Fusion 360, if I make changes, as long as the orientation of the bodies doesn't change, I can re-export and then replace the bodies in here
No problem.
and change it as well. Yeah, and it's just eye candy at this point. Like at that point, you're it's burning polygons for no reason. But it looked great in Fusion, I'll tell you that.
Oh, you had the screws in it?
Oh yeah, here. Just
Now we can model a loose screw or what happens if it scrapes against the wall.
Excellent, for those 0.03% of the time.
Yep. So, here's the one that I exported. Here's the one that I prepped. That I painstakingly added in and made joints for all of the screws that I could find. By using the McMaster car interface to figure out these are probably M4, these are probably M2.5.
All right, I shouldn't have asked.
Oh, yeah. Well, okay, and this probably explains really well why I spent 2 weeks importing a step file instead of there as a OCD perfectionist.
That was a step file versus
Yeah.
the step file comes from the Unshape or
The step file came from a OneDrive link that the Unitree folks have been passing around that someone added to the hacker group. So I'm not 100% supposed to have it. That's why I stopped short of publishing anything.
But the step, it's a model file format. Is that what step is?
Yeah. So it's it's by contour, so it's a far richer format than
Contour.
when you export to facets for 3D printing.
Oh, so it's designated, it's curves.
But
Curves.
yeah. I added in all of the screws for all of the screws for all of the motors. I added in the screws for the bolts. Let's check out the butt for a minute. I added in all the screws for the top. I added in the screws that were missing here. Because if you're going to do it with style. But the way that I imported it into Omniverse, there was another setting that someone showed me later involving joint origin. All 150 screws rendered in Omniverse to position 000.
So it's not worth it.
Not worth it, but yeah. So I'll probably try again because it makes it look a little bit better. But yeah, there's even without a two-way workflow, it's just a joy to work with.
Are you going to share all of your work with the community? Or?
Yeah. So here's the way that I'll word it because I'm not 100% that the step file was supposed to be distributed. If this excites you and you want to get in on it, let me know and I'll get you a copy. I'll share my USB scene. I'll share that, whatever you want. And just like I did with my InMove back in the day, is that chances are all of this is going to work out and we're going to have a physical robot within the next X number of months. And if this excites you and you develop something interesting with the simulator, let me know and we'll run it on the dot. Like, I mean, there's no reason this has to be a solo thing. And your cost to entry to developing for this is just a desktop or a laptop with a recent RTX graphics card on it, which I think is pretty cool.
What is your simulator goal? What's your tipping point when you go and you order the robot? So when I get it to stand up, when I get it to walk, when I get it to explore.
Okay, yeah, that's a good question, and hopefully I stick to it. There's two criteria. Criteria one, the main clear and present is these smart dudes need to be able to crack the Go2 firmware to enable programming on any level of dot. It's very easy to get into the system on a module. We know a lot about it. We've got the passwords for the logins. So the possibility also exists is that I just wipe their crap and write everything from scratch, which is possible, but yeah, it's a lot of extra time. But if they're able to crack it and open up the ROS2 interfaces so that I only interface through ROS and cycle in VBS, which is a very performant one. There's an Ethernet port on the top of the dog for the backpack, like it's all very tightly things. So if they can crack that and I just have to interact with the dog through ROS, that's the first one. The second one is I have to do something interesting that's worth running on the dog. Right, and standing up is just a hello world. That's just like the proof that it works. Getting one of the walking platforms or digging into one of the neural reinforcement learning. Or there. Once I do something interesting, probably when I hit this one, that's when I'll press the order button and get it.
But even you're ordering just even the cheapest one is 2,400, right?
Minimum, yeah. They're guessing import duty is 25%.
So
Now there's like an extended battery that's $200 more. So during the ordering process, if I can get them to put in the extended battery, then it comes to $2,600. I think that's worth it. The $280 controller that requires a smartphone to visualize on it, I'm not interested in that.
That's just a remote control thing.
Yeah, that's like
Although
20% of the cost or 10% of the total cost of the dog. It's like
for a remote control,
yeah, and you can just do it.
you can do it with your PC. Or
yeah. So
or with
for development in this hypothetical future, build a stand, hang the dog from it, and then just plug the Ethernet cable from the dog into the back of the computer and use the computer as a backpack, right? That's the minimum, because you don't want to damage the dog anymore. Or maybe just like hang it off of a lift or something, just until you figure out.
Until you get it working.
In all your videos, these guys are running around with a hand tether.
Yeah.
Or different robots, it's the same idea.
Yeah, and just earlier this year, someone posted a video, a graduate student that had an Go1 EDU, and she wanted to redrive a walking around further. And this gal is way smarter than I would ever be, and it's a 20-minute clip, and it's tough. Like at the end of it, she can kind of get it to walk. Now, as fun as that would be, I want to leverage other people's hard work as a starting point. So integrating that CHAMP framework will probably work for me.
You see, that's the coolest thing about it. That's one of the most motivational reasons to get real hardware this soon is because of the CHAMP and the Cheetah code base, right? Because otherwise, and you hear Chris Alberts talking about that a lot, right? I mean, on our forum, is that without that code, you're looking at a lot of difficult development, like graduate level, right? I mean, so, or just like hard coded, but with that code, you really have a shot at doing something in a hobby level time frame, right?
Yeah. Dr. Bruce said it best a couple of years ago. Like most of us, we're not researchers, we're integrators, right?
Yeah.
And I love that. The fact that the Cheetah code's MIT license, the fact that Omniverse Isaac Sim is a free download.
I want people to think.
Yeah, to quote 2-minute papers, what a time to be alive. You know?
It doesn't, yeah, you don't have to be in MIT or, a CMU or some research lab to be able to do something in a simulator and maybe even, a real hardware if you can afford that.
Yeah, so that's all I got this month. I'm excited to see where this takes us next month. And
Awesome.
all right, really cool. All right, thanks.
Wow, Andrew. Thank you. He spent his break doing that. I was seeing relatives and driving to Monterey. I wish I had more robot time, but family intervened.
All right, so let's break for lunch and just come back at 1 for our business meeting, elections, and let's move on to show and tell. With starting off with Jim, you're up first.
All right, thanks. Well, first I wanted to just share this article that I which I think everybody, I mean, it is in the Servo magazine, and it's behind a paywall, but maybe I could, maybe at least I can show you this, and maybe, if you do subscribe, you'll have access to it. Maybe I can copy some of the text over, but it's interesting because it's about the future of hobby robotics, and they're talking about an inflection point, or what I call that, or a critical junction in its evolution, because you'll see here, we were just discussing vintage computers. There's the Kim right there, and they're talking about in the Altair, and then on the next page is the Apple II. This was my progenitor here.